Alright, draft physics video, second try. Didn't I gotta learn my camera thing, but I'm not gonna turn a second camera on. So I lost the video, but shit happens. I was only halfway, well, quarter of the way into it, so it doesn't matter. Anyway, so it's just this basic theme of the whole, how physics got broken with all this Einstein bullshit with the whole bend space and now once he made bent space, now he can bend photons in it, and it's just such a mistake. I mean, he got the fact that, okay, photons don't care about what movement you have. They're always going to leave you at the speed of light, and but the whole idea of saying that, but in my special bent space, I can give them a second velocity. I can make them go in two directions, and that doesn't cause any kind of problem because I'll undo it. With the same non-existent bent space force, I will cause something, and then with the same non-existent bent space force, I will undo what I did. And it's just, it just was the biggest cheat in physics, was to take all of the forces of, to take the force of gravity and turn it into a non-force, to turn it into bent space. I mean, it was just such a disaster. Take it right out of physics, the physical world, and put it in this silly dimensional bullshit world. And that was just a colossal disaster. And then, like I said, it just don't, once you do this, it's like the Heisenberg thing. Once you create some kind of nonsense, it'll explain everything. And you can see that with dark matter now. They're using it everywhere. It's just super glue. And these things just become, these bad axioms just become super glue for anything that looks a little strange. We'll just blame it on the dark matter, blame it on the bent space, blame it on the Heisenberg uncertainty principle. Just throw it somewhere and we won't have to think about it and actually understand what's happening, because we can just fix it with a bent space. And that's what's written all over this crap. I mean, I've tried to explain in simple terms that the universe has elements in it that are different. They're different for a reason. So it's like you have the idea of these compressed bodies, these round spheres, and dense spheres like suns and planets. And then you have this other weird thing, this galaxy that's flat. Solar system, kind of flat. Very different. We don't have solar systems with stuff going all the way around them. So somehow the dense bodies don't function exactly the same as the collective body. They have a different dimensional function. Somehow the galaxies are only functioning in 2 dimensions. They're really not doing the 3-dimensional thing. And in, I would argue, the quantum world, it's reversed. The little bits are doing the 1-dimensional thing, going the speed of light, magnetism. These things are being, these things are forces, and the forces don't get bent by anything. They don't get bent by each other, and they just don't get bent. They have to be diffracted. They have to bang into something and get readmitted in some new way, new manifestation. Magnetism goes in, the wire remakes magnetism and sends it back out. It doesn't, there's no simple reflection. There's no way to convert its momentum except a physical conversion. Turn it in a harsh way. You can't give it velocity in some other direction and combine the two. You can't give it acceleration in some other direction and combine the two. So it's number one, it's just a violation of the speed of force, the speed of light. So I've said these things before, that light should have never been given the qualification of a speed of light. It should be the speed of force, because all the forces move at this speed, including bent space. I mean, that sounds pretty stupid when you say the speed of bent space, but it's true, and people don't understand it. Bent space has the same speed as light. Okay? That's how it works. Gravity works at the speed of light. Space bends at the speed of light. And doesn't that say something to you, that it's maybe this distinction of space is kind of silly? It moves the same speed as magnetism and light, and yet we're going to make a separate dimension with separate little gooey silly rules. So anyway, Einstein, he certainly understood that you couldn't make a photon go faster by running really fast and then shining your flashlight, yes, the light comes out the same speed. It's always the speed of light. But his rules basically violate that in the sense that, oh no, well, we can't make it go faster, we can't make it go slower, but I can give it another velocity in another direction. And I don't think Einstein actually thought of it that way. I think he thought of it as an acceleration in another direction, but it's the same difference. And you really can't play this game of, well, I have fake energy that I accelerate it with, bent space, and somehow I'll use its old momentum to get it out of the bent space. And so it's a fake energy going in and a fake energy going out. And so yes, of course, if you're using fake energy, you don't have to actually push anything. You don't have to have an actual force that pushes the Earth, right? The Earth just rolls, and then it can just roll right back out again, and there's no forces required. Well, we know in the quantum world, none of that shit works. You can push something into something, but if you want to push it back out again, you're going to have to apply a new force. You're not going to get this free ride. And that's all this is. All this amounts to is, bent space allows the fundamental conservation rules, in a sense, to be broken, because it doesn't account for the fact that these are opposing forces. And a photon can't carry extra momentum, and it would take extra momentum for it to, pop out. So it's just so corrosive. Bad axioms just ruin it, and I've already listed them. But push pull, they chose the wrong one. Wave particle, they chose the wrong one. What's the other one? But they're all over the place, and it just breaks the function of their physics. And this idea of giving a one-dimensional elemental particle, and they're clearly all one-dimensional. I mean, all the forces don't interact with each other. You can't bend magnetism. I mean, I don't think anyone's realistically thinks you can put magnetism in a gravity well and bend it. Magnetic lensing, is that where somebody going to come up with magnetic lensing next? I don't, well, we'll see. Once you break it, you can break it all the way if you choose. Then we'll have quantum lensing. We'll have the quanta do lensing tricks. I suppose there's going to be some place where they're just going to run into a brick wall where there's just no way they can explain the phenomenon that way. They'll finally find a place where the paradoxes will get too outrageous, and they'll have to concede it's a silly idea, giving this elemental particle two velocities. And as I say, Einstein might just argue it can only gain acceleration, but you can't. There's no rationale. You can't say I accelerated it, and I don't have to account for where the acceleration went. Because I'm going to pretend gravity took care of it. The bent space thing undid it magically. The bent space magically undoes the acceleration I gave it. It doesn't have to, in the Newtonian terms, encounter another force. What do I say about that? So there's some comments here I'll read. I did have watched a little bit of Hathaway's old video, and it just starts off. He's just applying momentum equations to photons, because he doesn't see them as different. To him, they're three-dimensional particles that they can acquire, like we acquire velocity. I've sort of, I've given you an indication here that I believe we're right now full of just photons, essentially, tons. And they all have momentum in all three directions, and we're just being, we have all this force constantly radiating out of us and radiating into us. It's just an exchange of polarization, and that's what keeps us together. We're just a pattern in the quanta. The ones we possess are of a certain polarization, and they react to each other in a certain way, and they're held together by the other quanta banging into them by certain simple rules. And so we can move in three dimensions, because we can acquire force. We can acquire actual arrows, actual extra stuff moving, and that'll keep us moving in a direction. And then we can acquire another direction, and then we can acquire another direction. So we can move in those three dimensions by just collecting extra stuff and going where the extra stuff takes us. A photon can't do that. A photon has one direction. That's it. It can't do two directions. It can't hold force in any other direction than the direction it's moving. It can't possibly have an acceleration sideways or a velocity sideways. It's insipid, in my opinion. It's obviously nonsensical. Forces don't do that. They're not baseballs. You can't throw them from a train and watch them bend with your momentum. Alright. So yeah, I mean, I've tried to explain. I mean, it just doesn't seem that complicated, you know. We look at the big universe, we see it has different rules. The little round things behave differently than the flat things. And it's almost like they don't even obey those rules, because that's the whole concept of gravitational lensing, is they've created this canard that galaxies have tremendous gravity. They're completely full of empty space and flat. You know, yet they've made them mega gravitational. How is that? They're less dense, you know, per atom, per space divided by atomic weight. So take the total volume and divide by the atomic weight. They're 1,000,000 times lighter than the sun, and yet they have 1,000,000 times more gravity. It's not obviously insane. No, I mean, insane is probably excessive, but I'm just saying it. I think this is imbecilic for scientists to argue this kind of nonsense. Alright, so I'll go to this comment and then we'll do some more fun with silly videos, you know, I guess. I mean, I watch them, so I might as well critique them and play some of the silliness. No point enduring the horror without sharing it with you. So, alright, so this mindless marble guys asked a couple questions. Alright, so my quote: I will create a beam of light that flies into the future on this perpendicular line faster than the speed of light. No, it will still go the speed of light, just that it will go off at an angle. Well, you can't have it both ways. So I'm just going to explain this one more time, but look, there's a hole in the, let's put a hole in the ship, okay, perpendicular to the light gun. Your objective is to get the light through the hole. You're going half the speed of light, which it means this hole is going to move half the speed of light. So you're going to fire light here. It's going to have to acquire this distance, and at the same time this hole is going to be moving away from it. Now you're saying, okay, it does go towards the future. It does go towards the hole, where the hole will be in the future. The hole is going to move here. You're going to move there. This gun's going to move there. So, but you have to shoot there into the future. And you're saying, oh, it does travel that line. It just doesn't go far enough. It can't go through the hole then. Then it ends up hitting here. It ends up short. There's no, you can't say, I'll just pretend the diagonal doesn't mean a longer line. It necessitates a longer line. The only way you can get to the hole is to travel the longer line. So, I mean, just, you know, okay, go ahead, make up whatever rules you want to make up, but I'm just saying it's a made up. Alright, what law of physics permits you right now taking a laser beam, moving it really fast vertically, and having the result be the beam will travel the perpendicular. Light doesn't travel straight. Okay, no, it does travel straight, but only at an angle. Well, again, the straight meant straight from the point you shoot it at. So, I mean, it's, again, just playing games with words. Okay, you can play that game, but you're basically saying it's wrong-headed, and now you have no explanation for why it's wrong-headed. Why can't I just tilt the light? If the light machine's producing light crooked, well, I should fix that. So I'm going to fix it, because the light machine, I want the light machine to shoot perpendicular. That's one of the rules. If it's not shooting perpendicular, it's not really doing its job, so it's broken, so I'm going to fix it. I'll just bend it correct. I already said this. What do you mean you said what? but the process that creates the light will be skewed when it is moving upward. So again, so you're saying that the extra velocity somehow skews the laser pointer. So if I move a laser pointer 5 miles an hour, it skews. I move it 50 miles an hour, it skews a little bit more. I move it 600 miles an hour, it skews a little bit more. I move it half the speed of light, it skews that much. Well, that's sort of my argument, right? I'm the one with the argument that force means, velocity means you had to acquire force, which means your system is very, very busy and very, very fucked up. But I'm still saying the rule is, whatever skewing there is, I'm compensating for it. So no, there's none of this, it shoots crooked shit. It shoots straight. That's the rule. If it doesn't shoot straight, we're not shooting the ship. Alright? But I'm just saying there's no real theory here except for you saying, well, okay, the magic electrons know to shoot ahead in the cells. Why wouldn't the electrons be broken in the way where they shoot the light backward? How do you know electrons somehow know how to shoot light forward? Because they're moving. What's your mechanism for that? And that doesn't sound like time dilation. That sounds like velocity degradation. That sounds like the matter's changing because of the velocity. That doesn't sound like a time dilation thing. That sounds like a human being change thing, clock change thing, laser beam change thing. That sounds like matter being affected by velocity. That's my theory. Alright. This has nothing to do about the future. Well, it does in the sense that you're going to arrive at a place. And at the time you shoot the light, that place is in the future. That's my argument. It's a simple argument. So the future has something to do with it in the fact that you have to shoot for that future if you have any hope to arrive in the present, the future present, with a light in the right place. Okay. Let's see. This is about the fact that your device is affected by its motion. So, that's my argument. Once the light is created, it goes in a straight line. Again, how does that explain? If it goes in a straight line perpendicular, it's not going to get to the hole. So again, this will just end up being circular, right? You're just going to keep saying, well, it is a straight line, it's just crooked. Whatever. If the light is emitted at an angle, which it's not, it will take more time for it to get to the top of the mirror. Huh? If the light is emitted at an angle, it will take more time for it to get to the top mirror. Well, there's no mirror in my example. By the way, but its speed of light is preserved. Huh? Yeah, sorry, I can't fix that no matter how much I think about it. Alright, this has nothing to do about the future. This is about the fact that your device is affected by the motion. Once the light is created, it goes in a straight line. I thought there was some part in here where he said it is going this... maybe he edited it. Yeah, it is edited. I don't think I changed from the last time I read it, though. I already said this. What's going to create when moving upwards? I thought he said somewhere in here it does move perpendicular. It just goes slower. Well, anyway, it doesn't matter. Maybe that's the first line. I'm a little tired, so... Alright, I'll try to read this again. If the light is emitted at an angle, it's emitted perpendicular to the ship. It will take more time for it to get to the top mirror. Why? By the way, because its speed of light is preserved. What does that mean? It takes more time, yet its speed of light is preserved. Catch-22 much? It doesn't follow the mirror. Like again, there's no mirror, but anyway. It's that the device shoots it at an angle. For fuck's sake. Again, alright, so you're going to just keep telling me the device shoots at an angle. And I'm going to say, and you're saying I can't compensate for that angle. It's impossible to compensate for the angle. So, as you speed up a laser pointer, the light knows, so I have a laser pointer pointing this up. The laser pointer, the electrons somehow know to shoot the electrons forward. So whatever speed I go, they shoot more and more forward. This line gets, this line gets more and more arced. And that's your answer. Somehow the magic electrons will not allow me to shoot light perpendicularly. Whatever. And I'll just point out again though, if they do shoot it perpendicularly, you're still fucked. So I mean, this stupid explanation that the light automatically goes forward doesn't fix the problem that if you don't go this full distance, in the same amount of time light travels this distance, okay, you're not going to get through the hole. The hole is here. Alright? You have to travel the full distance to get to it. You're not going to go through the hole in the side of the ship unless you travel the speed of light to do it. You only have so much time. This is moving away at the speed, half the speed of light. That can't change. So if you don't go this distance in exactly the same amount of time, which means you have to go faster, it ain't happening, buddy. Alright, tell me what's wrong with this, please. Well, what's wrong with it is you just make these declarations based on what fact. What physical fact gives electrons the knowledge that they're moving forward at a specific speed, and now they must shoot photons at an angle they never shoot them at? Alright, I'd like to know the answer to this as well. Well, whatever. The answer is I don't hear anything to argue with. Okay, I'm saying that they haven't said anything that changes. These are facts. If you're going to give something velocity, you're going to have to explain where it lost the velocity. So you tell me where the forward momentum, the photons don't go at an angle. The argument being made is they're moving this way. It's the baseball argument in the sense that if I take a frame-by-frame picture, the baseball's traveling not well, that's a bad example, the baseball, because it is traveling unstraight. I'm arguing that the photon travels dead straight and it hits behind the hole because it can't do otherwise. The hole went away, the light hit behind, and the photons did exactly what they're supposed to do. They went in a straight line in space. That's what they did. Your argument is they carry the momentum of the thing moving, and so therefore they're moving in a direction, and they're going to continue to move in that direction. So the first ton is heading out, and this is where it goes in, let's say, 1 second. And then the next second it gets to here, and then it gets to here, and then it goes through the hole, and it gets to here, and it gets to here, and it gets to here, and it's constantly moving this way. So even though it's going the speed of light this way, it's also going some speed this way. That's what you're arguing. And I don't see how you can get out of that scenario. You just create a photon that theoretically is going faster than the speed of light, and as long as I just turn this device this way, I can shoot light faster than the speed of light, because there's no way it went through the hole otherwise. And where did it lose its velocity? Where did it lose the momentum you said the ship gave it? The ship gave it momentum. It has momentum here in both directions. It has momentum here in both directions. It's moving the speed of light this way, and it's moving the speed of light, whatever the speed of the ship is, this way. And same here. It's moving the speed of the ship this way, and it's moving the speed of light that way. That's where did it stop? Where does it stop doing that? Where did the opposite force, where did the force stop it from having the extra momentum? Okay. Yeah, I can't argue it any better than that. I mean, you're claiming it acquired momentum, and then you decided it just went away, and it's not doing that anymore. Well, where did that happen? Where does that happen? Where's the boundary line for this magic I lost my momentum trick? Okay. So back to this craps. It really is horrible. Alright, so this video I don't think there's much point in watching. It wasn't all that interesting. Best of science. But just all this dark matter crap, it's just, it's just all made up, and we've already been over it, so what's the point of that? This is just a channel page, so this one was just horrible. So yeah, we'll play this. Well, this one was terrible too, but yeah, we'll play this one because this is just so bad, so bad.
Viagra single pass.
Oh yeah,
so
really.
guys with ED can take Viagra.
Yeah, it's fun having ED. You just snap it, it's no problem. ED. Guys with ED. Yeah, like my hubby over there. Yeah, limp dick. Yeah. I guess I'm not hot enough.
Vast and mysterious. To uncover its secrets, we use telescopes like Hubble.
Yeah,
but nature has some tricks of its own.
Oh yes, I'm sure it does. Tricky little nature.
That mean we can see very faint and distant galaxies.
Look, we make them all movie.
We wouldn't be able to see.
La 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 la.
Now, Hubble has produced some of the very deepest images of the universe ever. But even these extraordinary images have...
You are extraordinary, eccentric people.
their limitations. We know that there are galaxies that are simply too distant and therefore too...
He's like he should be doing a cooking show, you know? Sorry.
faint to show up even in these extremely deep images. So, what can we do?
We can just make up crap. Little stories, little three pig stories, little, you know, Hansel and Gretel were skipping across the universe and they tripped on a, you know, Little Miss Muffet's puffin.
Well, we can either build a bigger telescope, or we can be clever and use one of nature's telescopes. I'm talking about a phenomenon called gravitational lensing.
I guess I should speed this up, as this is just a little bit, I mean, it's only 8 minutes long, but it's 6 minutes long, but man, it's really just dragging along here. Yeah, we get this part. The part is here is your lines. You see these lines? Let's pretend those are the lensing lines. They separate at preposterous dimensions, the inverse square law. So, you know, this one's twice as thick as this one. This one's half as thick as that one. And it just gets, you know, it's... How can they possibly bend light to one location? How can light coming into them essentially parallel end up at the same place when the gravity's preposterously different?
Take something like a galaxy, full of stars, gas, dark matter, and dust.
Dark matter and dust. See, they just talk about dark matter now. It's just part of the vernacular now. It's like bent space. Yeah, oh yeah, no, we all buy this one.
This galaxy's gravitational force is so enormous that it affects the region it sits in and distorts the very fabric of the solar.
All right, so this is the argument right now. I mean, I hate to tell you people, but they're saying this has enormous gravity. It has no density. Okay, look at all this black space in here. Look at all this black lines, empty space. And most of these things are hydrogen suns. They're not even, to start with, they're not all that heavy. And so you have all this space between them. Tons and tons and tons of space. The gravity next to these little suns is stronger than the gravity of this galaxy. This galaxy has no gravity. It would take you for a really long time. If you stepped on the outside of the galaxy, it would take like 1 trillion years for you actually to get pulled into the damn thing. That's how weak this gravity is. There's no physics that can make this strong gravity except for the fact that they're claiming that all of this stuff, all these empty spaces are all full of a fake dense matter like invisible lead. This galaxy is made of invisible lead. Yet there's no indication of everything flying into each other. So even though there's invisible lead right here, none of these stars are smashing into here really quickly. They're not getting pulled in by the invisible lead. I mean, it's just such a... How can they call this science? This is just such propaganda.
In space. It isn't only galaxies that do this. Any object that has mass distorts the space around it with its...
Well, I mean, again, you really have to be sensible about it. Any object that has mass, okay, so the photon distorts the space around it, and does that attract other photons? Apparently not, because photons don't crash into each other. So even though the photon is distorting the space around it, it doesn't create enough distortion for 2 photons to ever hit each other.
Gravity, from large galaxy clusters down to individual stars.
In space, light travels invariably along straight lines. But what's a straight line? Well, it's the shortest distance between 2 points. But in a curved space, the shortest distance between 2 points may not necessarily look particularly straight to us.
Yes, well, that's just so brilliant, right? I mean, what a bunch of crap. It's not, the straight line isn't necessarily all that straight. Yeah, science is fun. Because we can say words that don't mean a motherfucking thing anymore.
And what that means is that when a light ray passes very nearby a massive object that curves the space around it, the light ray is bent. As a result, the
Okay, so this is how they illustrate this canard, with this vacuous presumption that somehow, oh look, see here, these two little lines just come in here. So let's pretend that the thickness doesn't matter, so there's no degrade in the gravity at all. So it's the inverse square law is what's bending this light, and it just doesn't matter because that doesn't change quickly. And we're talking about an inverse square law where it changes radically in high gravity. I mean, it's the difference between just that little first 1 R of change. You go from something like 70 to 15 with just 1 R, 1 radius.
object, or rather the curved space around it produced by its gravity, acts like a lens, a gravitational lens that deflects.
Okay, so this is it. I mean, what is this crap, right? They just make this stuff. Okay, I'll just show you an image and I'll say lens galaxy image. Lens galaxy image. See them? They're perfectly round. That certainly makes sense. Who knows what all this stuff is here, right? So you have all these crookedy lines, which is, you know, you have straight lines. This is what they're going to use as an argument. You can actually form, even galaxies are pretty much, you know, roundish. You know, they really just don't do, like, here's a little bit of a straight part. They don't do hexagons. I mean, why all this deformation in the gravity? And this is deformation in the gravity.
Light into our telescopes that would have otherwise never made it there.
So, and look, there's just no symmetry at all. And what's the R? Like, if this was the gravity here, I mean, this gravity is pathetically weak out here. How is this lensing? And again, why isn't everything being sucked into this thing if it's so powerfully gravitational? No explanation. What's this thing? It's got a tail on it, you know. Is that lensing?
This deflection.
Here it is again. Here it is some more. We'll make them in motion, so everybody gets the idea that, hey, look, the universe is all twisty-turny. But look at this. You got a little straight line here. You got straight lines over here. You got those straight lines over here. Lensing?
That distant and faint objects can suddenly be seen peeking from around the edge of a nearer lens, although they may look quite different.
Okay, so they're saying this is a lensed image, apparently. I mean, look at the detail in this thing. Okay, so you got R squared change in the lens. I mean, it's a hugely distortive lens in the sense that for every little bit of movement here, you're got a completely different angle of reflection. And yet somehow that's coherent to the actual placement of this thing back in space. That you can undo, but with that huge amount of distortion, somehow this still has a swirl in it. Oh, please.
Unexpected.
And again, look, what's all this stuff? What's this? What's this? 400 million lenses?
We see distant galaxies that have been lensed as arcs on the sky around their lenses.
Yes. So again, as arcs in the sky around their lenses that aren't anywhere near proportional or even. So even though it's a spherical body, we don't have any presumption that it's oblong or weirdly shaped. It can create squares, straight lines. It can create curve here this way. This one will curve more out this way. This one's curving more out this way. All kinds of deflections. Perfectly reasonable. There's nothing bullseye about gravity. No siree. It doesn't obey any of that kind of like bullseye rules.
For example, the arc around this galaxy cluster is not a photograph.
Okay, so look how thick this is. So just recognize the thickness. That's the only thing I want you to really appreciate is the thickness of it. Because the change, this is hundreds of light years across. the change in the gravity from here to here has to be frickin' enormous. And yet it's all in the same focus, and we're supposed to believe that this is an artifact in a lens. I mean, it's yes, it's just insanely stupid. I mean, and the giveaway is like I said, is they're doing this arc thing. Like, look, it's a circle. Well, if it was a circle, then the gravity has to be symmetrical, and that means it has to obey the inverse square law. If it was dark matter, how could it possibly be symmetrical?
Of an error at a second, more distant galaxy, deformed but visible. Or, if everything is perfectly aligned, we see a ring of light encircling the huge galaxy in the foreground. These perfect rings, known as Einstein rings, are so rare.
Okay, so she said perfect rings, right? None of them are perfect rings, not even close to perfect rings, and none of them are where the gravity is the strongest, which is closer in. So where you would expect there to be possible lensing, because there was enough gravity to bend light. Again, we're talking about bending light, and bending it a lot. Not a little, a lot. I mean, it can't get from behind this object, come out and get bent all the way to us without there being a ton of gravity there. I mean, mega gravity. And yet it doesn't obey the inverse square law at all. And it's clearly not perfect either. I mean, quite obviously there's no symmetry in any of these images. The universe, you know, the universe is kind of perfect in its mechanics. It doesn't just do this fudgy, like, I'll be a painter and pretend I did a circle. It does things really sharp and mechanically. There's no room for this as a phenomenon of gravity. It's a strict force. It doesn't do this slop.
But only a few handfuls have ever been
There, look at all that stuff.
observed in visible light.
So only a few have been observed in visible light, which means these are all radio telescope images of X-rays or some other kind of stuff, which I suppose doesn't really matter. It just depends on what they did to acquire the image in terms of enhancements. I mean, maybe the image is something like this, and they let a computer make it into that, and that's a little dangerous. But who, you know, I'm not going to make any accusations that they're, you know, deliberately creating this crap. But what point did I wanted to make some kind of point about this? But look at this one. It even has a loop in it here. How is that possible? I mean, there has to be, you know, so look at this stuff. I mean, you have to have some discipline and say, I'm going to obey a rule somewhere. All right, so here's a really primary point I want to make. We see all of these images over and over and over again. All these images. Some of these images are 10 fucking years old. How come we never see the same place in space taken from the two perspectives that Hubble has? That is, the two opposite sides of the sun. You know, the winter picture and the summer picture, if you like, or the spring and fall pictures. How, you know, wherever it has the perspective. Why don't we see triangulation of these locations? Because that'll demonstrate if this shit means anything, right? I mean, that'll tell you a hell of a lot. If you look at these places in space from two different angles, you'll learn a huge amount about what's in front of what and what's behind what, because all this shit's going to move around. So why don't we have any of those images? We don't even have images from the same location 10 years later. We're given nothing, absolutely nothing, as context.
A few years ago, Hubble observed an even rarer cosmic coincidence. An incredible double ring, where Hubble can see the light from not one, but two galaxies.
Oh, I mean, it's just an extraordinary extrapolation. So they're saying that there's one galaxy in front of another galaxy even further behind, and somehow the light could get past the first galaxy and then lens into the second. You know, I mean, they're just so desperate. And again, do it completely unsymmetrical. So somehow the symmetry of the gravity for this ring is different than the symmetry for the gravity for this ring, and somehow that makes sense, that somehow the gravity is not even though we know in every single physical circumstance ever really observed, the gravity is always symmetrical. You can't do ellipsoids in gravity.
Perfectly aligned behind a
Again, perfectly aligned.
closer galaxy.
Amazing.
Lensing can create weird and amusing shapes.
Okay, so look at all this stuff. I mean, it's all these, look at these dead straight lines. I mean, I suppose they won't blame that on lensing because they'll actually be smart enough to figure out that's a galaxy on its edge. All right, let's see. So we'll let it keep playing.
Take Hubble's image of galaxy cluster Abell 68. The central part of this image is distorted and stretched out into streaks by the cluster's lensing effects. But visible in the top corner is a cosmic space invader. This deformed
Yeah, that's just so funny. So yeah, I've seen this image.
galaxy is actually visible twice.
Okay, so, it has two eyes here. How come some got one there? And oh, look, it's there again. There it is again. It's being lensed. There it is again. There's another little orangey bit. I mean, come on. I mean, does this make... What, somebody can actually make sense out of this tripe? I mean, it's a perfectly formed galaxy. So it's in perfect focus at r squared distortion. So r squared distortion, when Fuji... comes out with the lens, it's got r squared distortion. Oh, everybody's going to rush out and buy it because, damn, that's a piece, that does one hell of a job. Look at that focus. That's one hell of a fucking image. Yeah, get yourself some r squared distortion.
As its light is following two separate paths around a nearer elliptical galaxy before...
Okay, and it's just made up galaxy because I don't see it anywhere. So the magical, really strong gravity galaxy is somewhere in here. Somewhere. Who the hell knows where? And it just poofs these perfectly resolved images with all kinds of detail in them. And nobody says anything. Nobody takes a pause and says, wait a minute, I think this story's gotten silly. I think you have way too many you got 5 pigs in this story. It's way too many pigs.
or reaching us.
Oh, isn't that cute?
Now, a gravitational lens not only distorts the images of background sources into funny shapes.
Well, apparently it didn't distort that one at all. I mean, in the one image looked like a perfectly normal galaxy to me.
But it actually makes them brighter. That means that when you...
Yes, which that also makes a lot of sense. So it's collecting extra light from by having an r-squared deficit in the amount of bending to get to us. So almost parallel light comes in and it's heading to us and we're almost parallel in a sense, but we're not. But it has to bend. I mean, it has to really bend dramatically. It has to bend at the point of the lens. The arc, the angles going in and going out are humongous.
Using a gravitational lens, we can actually see fainter and therefore more distant objects than would otherwise be possible. Also, the images are magnified so that we can see more detail, just like when using an ordinary magnifying glass.
Right, it's just like that. I mean, when I use an ordinary magnifying glass, I'm about, a foot from the glass, and the subject is either close, or if I go with far away, it gets a little more complicated because I have to really smash it against my eye, and that doesn't do any magnifying. But the whole idea is that the lens collects the light. It's called collector. And all you're doing is collecting light in a tiny, tiny piece of the lens. So how can you magnify the brightness in that tiny little piece of lens? Come on.
This isn't the only.
I mean, the whole point of telescopes is, even Hubble has like a 2-meter mirror in it or something. It's got a pretty big mirror. I mean, the whole point of the telescope is to collect a whole bunch of light. And yes, I know this is supposed to be a big giant galaxy and this is only one little spot and all that kind of crap, but you're actually focusing on that spot somehow, that spot is collecting, well, I won't even try to explain because it's, getting into this whole converging, diverging light argument. the idea is to collect light that your eye couldn't collect by making the eye bigger in a sense, and then taking the big image and making it small so your eye can put it inside your brain. It's like you're just taking big images and making them small. And how does R² gravity do that?
Intriguing effect that gravitational lensing can produce. Take these 5 quasars, photographed by Hubble back in 2006.
Alright, 2006, and we don't have an update picture. Okay, cool. But look at the other artifacts in here. All crookedy. Yeah.
They all look very similar and close together. Perhaps a little too similar. In fact,
so they'll have a picture here.
These are not quasar quintuplets, but a single quasar seen 5 separate times as its light is lensed by a huge cluster of galaxies lying in the foreground.
Right, so somehow a huge cluster of galaxies that we can't see. I see a bunch of empty space, a little thing here. R² gravity is almost zero gravity here from this object. There's no way there's any gravity from this object. I mean, it might as well be you could make it into a can of tuna fish. I mean, it's irrelevant out here. And yet it's strong enough to create circular things that actually, and they're so bright, they actually have those little crossy lines, which only happen when you have a really, that's like an over brightness issue. Something so bright that it flares the lens on the camera. The Hubble telescope is it's so much light, it's diffracting it on the inside of the telescope.
While bizarre, this multiple imaging can be very useful to astronomers and allows us to figure out how...
So again, they talk about this usefulness, and yet they don't have a second image from any location, which might make it useful. If you know where a lens is, maybe you could use it from different angles to see different things, and there's no conversation about using it from different angles. So again, why not? I mean, it's obviously a fairly substantial focus point. One side of the sun versus the other side of the sun on the Earth's orbit. That's 16 minutes at the speed of light. It would take 16 minutes at the speed of light to get from one side to the other side of the Earth's orbit. And if you go the long way, it's like 22 minutes. I mean, it's a long way, fuckers.
Light from the distant object has traveled to us. These weird cosmic doppelgangers can be used to explore both the characteristics of the gravitational lens and the universe itself. For example, how it is expanding.
Alright, so now they're just going to talk complete bullshit with their
Hubble's
synthetic
Frontier Fields
images.
observing campaign, which began in October 2013, will combine the magnifying power of gravitational lensing with the light-collecting power of Hubble to delve even deeper into the distant universe.
Yes, and we'll just make up some more silly stuff, but we won't ever take a picture of the same place twice from 2 different angles, because that would make the jig is up.
So, watch this space. This is Dr. J, signing off for the Hubblecast.
Oh, Dr. J. It's very trendy. Not. Thank you very much. But I've had my fill of this crap. That was just so bad. This one is really... Maybe I'll save this one for later. Yeah. I mean, it's just a computer voice. But real... Oh, just, still doing this Einstein ring. Like, this makes any motherfucking sense at all. It's lensing through a giant fireball. Yeah, sure it is. This is just so bad. So, oh yeah, I did do the Degrassi Tyson Star Talk. Oh man, so bad. Right, yeah, I did that too. Yeah, I'm running out. I mean, we're getting down into the real crappy videos pretty quick. So anyway. Yeah, I've probably had enough. It's just too pathetic. So, but you can see even in this little icon, this is a galaxy. And look where they have the light lensing. Yeah. Way out here. Okay, so till the next time and such.